In this lesson, we are going to discuss various ways to estimate integrals. So far we have found integrals by finding antiderivatives and plugging in the endpoints and using the fundamental theorem of calculus. But as you have probably noticed, finding an antiderivative is at best really, really tedious. All the problems that you've seen thus far have been doctored to work out. And there are situations in which you will actually have to use an approximation. So the first thing I want to talk about are two situations in which it is impossible to find the exact value of a definite integral, and you have to use an approximation technique. So the first thing is that when finding the integral from a to b of f of x dx, assuming that your function is continuous and all that jazz on a to b, it may be hard, or in some cases even not possible, to find an antiderivative. Of f. I haven't been withholding antiderivative rules from you. They're just our techniques. There are no hard and fast rules. And the second situation is one that probably is practical to a lot of the engineers, is that you may have a function determined from an experiment. So a function from an experiment. And you have data, but no explicit formula. And it's totally possible that you could say use those data to find a function, but in many cases, it probably wouldn't be very practical to do so, and you can just use the data to make an estimate. So in Calculus 1, you learned two estimation techniques when you first discussed integrals. You learned left sums, right sums. Those were the first two. And then you learned one more, which was the midpoint rule. So we are going to estimate the integral from 0 to 2 of e to the negative x dx using n equals 4. Now I chose an integral that we could actually work out on purpose so we could compute the error, as in like figure out how much we're off by. So the first thing is let's find that value exactly. So the integral from negative 2 e to the negative x dx, that's negative e to the negative x evaluated from 0 to 2, which is the same thing as negative e to the negative 2 minus negative 1, or 1 minus e to the negative 2. So that is the exact value, and just keep it, and we're going to use it in a second to check the error. So now this e to the negative x function looks approximately like this. It is a decreasing exponential. It goes through 0, 1. And so we'll say that this is 2. Now we're going to estimate it using 4 subintervals and a left sum. So divide that into 4 pieces. Delta x is the width of your interval. That will be 2 minus 0 over 4, or 1/2. And to estimate it, you say, well, I could just assume that the curve's height is about that much, the height at the left endpoint. And because this curve is decreasing, this will be an overestimate. So the way you notate this is you say L for left sum, subscript 4, meaning 4 pieces. And the first box, the base is 1/2. The height is e to the negative 0. The next box, its base is 1/2. Its height is e to the negative 1/2. The next one also base 1/2, height e to the negative 1st. And then lastly, between 1 and 2 is 1.5, base 1/2, e to the negative 1.5. And it will be easier to put this in a calculator if you factor that 1/2 out. And then e to the 0 is 1. So 1 plus e to the negative 1/2 plus e to the negative 1 plus e to the negative 1.5. And that will be approximately 1.099. Follow web assigns the directions on rounding. I'm just going to round to 3 decimal places. Now we can compute the error in this estimate, so how much we're off by, and your book defines the error this way, so they call it E, capital E sub L, meaning for the left estimate, and we always find this using the actual minus the estimate. So the actual is the 1 minus e to the negative 2, and we're taking away the 1.099. And so the error is negative 0.234 approximately. And I know that this seems a little bit counterintuitive to me too, the way that they define this, because obviously that estimate is an overestimate, and why is your error negative? What this does is it tells you what you can add to this left estimate to get the actual value of the integral. So you take that left estimate and take away the error, and you add the error, which is a negative number. It takes you back down to the original. Error usually is described in terms of absolute values anyhow, so the order is not super important, but the important thing is it's the difference between the actual and the estimated values. Okay, so same idea but right sums. So the picture is pretty helpful. So roughly speaking, we look like this. So there's 2, there's 1, here's a half, here's 1.5. Now for right sums, look at each subinterval and you say, well, I could just go to the right point on the curve and make a rectangle there. So this will be r sub 4. And I'm going to factor out that 1/2 right away because I'm tired of writing it 4 times. So the first thing you plug in is a half. So 1/2 e to the negative 1/2. Plus then we'll have e to the negative first. And then e to the negative 1.5. And lastly e to the negative 2. And that's approximately 0.666. Now the error in this case, remember we're going to find that using the actual minus the estimate. So we'll say capital E sub r, and that will equal the 1 minus e to the negative 2 minus this 0.666, which is approximately 0.197. Which tells you that if you take this 0.197, add it to 0.666, it gives you the approximate value of the actual area under the curve. And I say approximate because both of those things have been rounded. Now, a much better estimate that you learned in Calculus 1 is something called the midpoint rule. In the previous example, the left sum was clearly an overestimate, while the right sum was clearly an underestimate, and one natural thing to do would be to average the two. But it turns out this thing called the midpoint rule does an even better job than averaging the left and right sums, which we'll actually discuss in this lesson. So let's draw a picture of what the midpoint rule looks like. So you have e to the negative x, halfway is 1, there's 2, halfway is 0.5, and then we have 1.5. Now instead of plugging in the left point or the right point, we're going to plug in the middle point. So in that case, the middle point is 0.25, and go up to that point on our curve. And notice how that estimate, despite my crappy picture, it also overestimates and underestimates at the same time. So halfway between 0 and 0.5 is 0.25. Halfway between 0.5 and 1 is 0.75. And look at how that box also sort of does a little bit over and a little bit under. Halfway between 1 and 1.5 is 1.25. And halfway between 1.5 and 2 is 1.75. So those are the numbers you're actually plugging into your function. And once again, the base of each rectangle is 1/2. So M4 will be 1/2 times e to the negative 0.25 plus e to the negative 0.75 plus e to the negative 1.25, and then plus e to the negative 1.75. And that's approximately equal to 0.856. And the most astounding thing here is the error. So the error for the midpoint rule, so remember that will be the actual minus the estimate, and that's 1 minus e to the negative 2 minus 0.856, and holy moly, that's 0.009. It is way more accurate than the left and right estimates, like light years ahead of it. So one question is that we'll discuss in this lesson is how do we determine how many pieces to cut the interval into so our estimate is sort of as accurate as we need it to be. Now another rule is called the trapezoid rule. Now this, instead of approximating the area by a box, it approximates the area by a trapezoid. So it takes these two endpoints, one at that end, one at that end, and connects them with a straight line. And this is what the rule says. You take delta x divided by 2, and then you add up f of x naught, 2 f of x1s, 2 f of x2s, 2 f of xn minus 1s, and 1 f of xn. So think about it, f of x naught is plugging in your first endpoint, f of xn is plugging in your last endpoint, and then all the other ones are the middle endpoints. And the question is well, why the heck is there just one of the first and one of the last, and 2 of all the middles? And that has to do with the area of a trapezoid formula. So the area of a trapezoid with base 1 and base 2, its area is 1/2 base 1 plus base 2 times h. Now what we have here are trapezoids that are on their sides. So that's base 1, that's base 2, its height is the distance from x0 to x1. So let's compute the trapezoid thing specifically for this thing that has 4 pieces, and you'll see where that pattern is coming from. So that's called T sub 4, T for trapezoid, 4 meaning 4 pieces. So first of all, this first rectangle, so we'll have 1/2. Now base 1 is f of x0. So 1/2 f of x0. Base 2 is f of x1 plus f of x1. And then the height is delta x. Similarly, the next rectangle, we see that one. Base 1 is f of x1. Base 2 is f of x2. So we're going to have plus 1/2 times f of x1 plus f of x2. That's the averaging the bases, delta x. So done this one, done this one. Next one, same idea, 1/2. Now base 1, which is this, that's f of x2. Base 2, which is this, that's f of x3. And the height there is delta x. And lastly, we'll have 1/2 f of x3 plus f of x4 delta x. Now notice here that the greatest common factor is 1/2 delta x. And when we take that out, we have f of x0. We have this f of x1, that f of x1, making 2 f of x1s. And then we have 2 f of x2s, 2 f of x3s, and just a singular f of x4. And 1/2 times delta x is the same thing as delta x over 2. So that is where that formula comes from. It comes from the area of a trapezoid. Now, another way to think about that trapezoid rule in terms of the left and right sums is that it actually is the average. So the trapezoid rule is equal to the left sum plus the right sum divided by 2. And if you think about it, the left sum does f of x naught plus f of x1, just with that 4 thing, ends on the f of x3, and it multiplies that by delta x. That would be L4. The right sum does delta x, skips the first endpoint, does f of x1 plus f of x2, and it does up to the last endpoint. So that's R4. If you add those up and divide by 2 to get an average, you get delta x over 2, and you'll have 1 f of x naught, you'll have 2 f of x1s, you'll have 2 of all the middle ones, and you'll have 1 f of x4. So when you thought, oh my goodness, I should just average those left and right things to get a new estimate, the estimate that you actually get is the trapezoid rule. So if you like this, you can just find the left sum, find the right sum, and then find the average. Of course, unless the question doesn't ask for the left or right sum, in which case it's easier to use the trapezoid rule. So use the trapezoid rule and the midpoint rule with n equals 5 to approximate the integral from 1 to 2 of 1 over x dx. And we're going to find the error in each approximation, so let's find the exact value. So the exact value, 1 to 2, 1 over x dx, is ln x absolute value we evaluated from 1 to 2, or ln 2 minus ln of 1, which is ln of 2. So we'll be using that in our calculations, but that is the exact value of this integral. And let's also find delta x. So that will be 2 minus 1 over 5, which is 1/5 or 0.2. Okay, so first trapezoid rule, t sub 5. So delta x over 2, so 0.2 over 2, which you could say was 0.1. And then first we plug in the first endpoint, so that would be 1 over 1 plus 2 times 1 over 1.2, let's plug in the next point, plus 2 times 1 over 1.4, plus 2 times 1 over 1.6, plus 2 times 1 over 1.8, and then just 1 times 1 over 2. And that's approximately equal to 0.696. And the error for that trapezoid rule will be given by ln2 minus 0.696, which is negative 0.003. So you're like, well, that's not so bad. Only 5 pieces and you're within 2 decimal places. Until you see how awesome the midpoint rule is. So there's the trapezoid rule. Now the midpoint rule. So first of all, what are the midpoints? For me, a picture really helps this. So I have 1 and I have 2. 1.2, 1.4, 1.6, 1.8. Those are the endpoints of my major intervals. Halfway between 1 and 1.2 is 1.1. And then halfway between 1.2 and 1.4 is 1.3. So M5, and this formula is just taking delta x times the sum of all the midpoints evaluated in the function evaluated those points. So that will be 1.2, which is my delta x, times 1 over 1.1, plus 1 over 1.3, plus 1 over 1.5, plus 1 over 1.7, and plus 1 over 1.9. And that gives us approximately 0.692. And the error in that estimate, which is ln2 minus 0.692, is just 0.001. Notice it's less than half of the error of E sub t. Pretty cool. And you wonder, like, so is that, so the reason we chose to estimate integrals whose values we could find exactly is to get a feel for what is the error going to be and how much are we off by. And a reasonable question to ask is like, well, is the midpoint's error always less than about half the error of the trapezoid rule? And the answer is yes. So these are formulas that you're not going to have to memorize. They're just things that you're going to have to use in your homework and your take-home quiz. So suppose that you have a function, you want to know how accurate is the trapezoid rule and how accurate is the midpoint rule. So what you have to do is you find your second derivative of your function, and you have to figure out a number that it is less than or equal to for all the values that you care about, so all the values of your definite integral. This can be done by graphing. Sometimes it'll be pretty obvious because the graph of the function will be something you know how to do. And it also is the case if your graph has sort of a weird highest point, you can just pick a number that's bigger than it. There's lots of correct ways to do this. So notice that the trapezoid rule and the midpoint rule's estimate formulas are almost the exact same, except for the midpoint's rule's estimate has a 24 in the denominator, whereas the trapezoid rule's error has a 12. Notice that this one, E sub m, is half of E sub t's. And these are also worst case scenarios. So your error is less than or equal to this value, meaning that this is the absolute worst it could be, but in all reality, it probably actually is less. So here's the question. How large we take n be, so how many pieces should we slice our interval into, in order to guarantee that the trapezoidal and midpoint approximations for this function are accurate to within 0.0001. So the first thing you have to do is get k. So get a k. And the way you get a k is you find the second derivative. So f prime of x is -1 over x squared. The second derivative is +2 over x cubed. And notice that on the interval from 1 to 2, this thing is biggest, as in the second derivative is largest, at x equals 1. So we can take k equal to 2. And so then we know that E sub t, absolute valued, is less than or equal to k b minus a cubed over 12n squared. And so plugging in our stuff, we have for k, we're going to plug in 2. B and a are the endpoints of our interval, so 2 minus 1 cubed over 12n squared. And we don't know that n. What we want is this expression to be less than 0.0001. That's what we want to solve. So I'm going to multiply that 12n squared to the other side, and I have 2 is less than 0.0012 n squared. Now I'll divide by that 0.0012, and I'm going to approximate here, but I get 1666.7 is less than n squared. And now since you've got positive numbers, you can square root both sides. And you get 40.8 is less than n. And n has to be a whole number, so 40.8 is kind of like the lowest it could go. And this function is an example of something that always rounds up. So we have to have that n is bigger than or equal to 41. As long as we use 41 terms or more, the error will be less than 0.0001. Now that's for the trapezoid rule. Now for the midpoint rule, so the error for the midpoint rule, same idea, same k. So 2 minus 1 cubed, but now it's over 24n squared. We want that to be less than 0.0001. multiply the 24n squared over, and we'll have 2 is less than 0.0024 n squared, divide by 0.0024, and you get 833.3, once again an approximation, is less than n squared. Root both sides and you have that 28.9 is less than n, so you have to have an n bigger than or equal to 29. So the pattern wasn't as simple as you needed like half as many terms for e sub n, but you do definitely need less, and if you were worried about how many operations a computer had to perform, picking the method that was accurate with fewer things would be the better way to go. So now let's use the midpoint rule with n equals 10 to approximate the integral from 0 to 2 e to the negative x squared. Now notice that this is an integral that you actually don't know how to figure out. You can't evaluate this one, it's not possible. You can try really hard to prove me wrong, but I'm pretty sure that it can be proven that this integral does not, when you antidifferentiate e to the negative x squared, there is no closed form sort of formula for it. It's not possible to antidifferentiate it at this time. We will learn an approximation technique to do so in chapter 11 though. So if we're going to estimate this, first let's figure out what delta x is. So delta x is 2 minus 0 over 10, so 1/5 or 0.2. And so m sub 10 will equal 0.2 times, all right, so our interval starts at 0 and then goes to 0.2. The middle point is 0.1. So we have e to the negative 0.1 squared. Be very careful that the negative doesn't get squared. It's not supposed to be. And then after that, between 0.2 and 0.4 is 0.3. So plus e to the negative, and then the 0.3 is squared. And then next we'll have e to the negative, and then 0.5 is squared. And you get the idea, just put a dot, dot, dot. I get that you have the pattern. Tell me what the last one is. So if your very last point is 2, 0.2 before it is 1.8. So the last number you plug in is 1.9, e to the negative 1.9 squared. And then use a calculator very, very carefully to estimate that. And it's approximately 0.882. Now, I don't want you to spend all your time finding first and second derivatives, so given that f of x is equal to e to the negative x squared, I'm just going to tell you that the second derivative is e to the negative x squared times 4x squared minus 2. And when I looked at a graph, so I graphed this function, and after graphing, I found that this thing is less than or equal to 1 on the interval from 0 to 2. So I'm going to take k equals 1. And I think it was actually just less than 1, not even less than or equal to. So the estimate for the error is less than or equal to 1, 2 minus 0 to the third over 24 times n squared, so 10 squared, and that's approximately equal to 0.003. Taking bigger k's just makes this a more conservative estimate, but remember that this is the absolute worst error. As in reality, your error might actually be less than that. So when we estimated the area under the curve with the trapezoid rule, we took these endpoints and connected them with a straight line. Now instead we're going to look at them in groups of threes, and we're going to fit parabolas through those groups of threes. And notice how close this parabola actually gets to the curve. Because the parabola is itself curved, it kind of gets the curvature of the curve down. The derivation of what the formula is, which is given above, is pretty darn tedious. You have to find a parabola that fits 3 points, which is not a super easy thing to do. But notice that there's a pattern that you have delta x over 3. So where that comes from, you'd have to go through the derivation to understand. And you have f of x naught and f of xn once, just like with the trapezoid rule. And then these coefficients in the middle, they alternate 4, 2, 4, 2, etc. So they start with 4, they end with 4, and then they flip-flop. And so what you have to understand is the basic idea of what this comes from. So the basic idea is this, is that you use parabolas instead of straight line segments to approximate a curve. And the other thing is that once you have a sort of parabola equation for a particular subinterval, once you've got that, you can integrate things that have x squareds rather easily. And the thing to note is that a line takes 2 points, a parabola takes 3. So that's the basic idea that you have to understand. What we're mostly going to do is use it. And it turns out that this rule is actually is more accurate than both the midpoint and the trapezoid rule. So use Simpson's rule with n equals 10 to approximate this integral. So first of all, notice that delta x is 2 minus 1 over 10, or 0.1. And so s sub 10, s for Simpson's, will be delta x over 3, so 0.1 over 3. And then we'll have first 1 over 1, and then the constants go flip-flop, 4, 2, 4, 2. So 4 over 1.1, 2 over 1.2, 4 over 1.3. List a little bit, although you got the pattern, all the way up to the last one to have a 4 is 4 over 1.9, and finally 1 over 2. And when you evaluate that, you get this is approximately equal to 0.693. Now, I said that we were going to talk about data, and we haven't even bothered, so now we'll actually do something where we don't have a function, we actually just have data. So a radar gun was used to record the speed of a runner during the first 5 seconds of a sprint race, so it must be some kind of sprint race. Use Simpson's rule to estimate the distance the runner covered during those first 5 seconds. So for me, I think it'd be helpful to put numbers here. 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. All right, so we have 0 to 0.5, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 11 points means just an interval of 10 subintervals. So this is s sub 10. Notice that the delta x is 0.5, so 0.5 over 3. And we have 1 times 0 plus 4 times 4.67 plus 2 times 7.34. And from the table you get the idea, so just write plus dot 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 plus. The last one will be 4 times 10.81 and then plus 10.81. So it appears that that runner got up to speed and their speed leveled off. And that's going to be approximately 44.735 meters. So that's about how far that runner ran. Now, what if you had a graph? So here's an example where you have a graph. And I think that there must be a typo here because I double checked this against the answer key in the textbook. This says hours, this says seconds, and R of t is given in liters per hour. I think that this label, this is supposed to say hours. There definitely are instances in which you would have to sort of change the units so that they do match, but this is definitely not one of them. This problem works out too nicely as is. So notice that this R is liters per hour, and the other axis is hours. So if you want to estimate how much water leaked out, the area under the curve tells you how many liters. And so we are going to find this assuming that delta x is equal to 1. So that's 1 chunk, 2 chunks, 3 chunks, 4 chunks, 5 chunks, 6 chunks. So 6 subintervals. So we're going to assume S sub 6 delta x equals 1. So S sub 6 will equal 1 over 3. And then first when we plug in 0, looks like we get 4. That's my x naught. Plus 4 times when you plug in 1, looks like we get 3. Plus 2 times when you input 2, it appears you get something like, I said 2.3-ish. On questions like this, WebAssign has like a tolerance for a certain amount, like how much right answers can be off. Next, when you plug in 3, so you get about 1.9, so plus 4 times 1.9. When you plug in 4, I figured that was about 1.5, so 2 times 1.5. When you plug in 5, ooh, say 1.1. I could buy that it might be 1.2. And then lastly, when you plug in 6, you get 1. And this is approximately 12.2 liters. And like I said, WebAssign, if you think that they counted you wrong when you weren't wrong, just let me know and we'll take a look at it. But they do usually have a tolerance for having some rounding error, having to guess what those values are. Now, I said that Simpson's rule was a much, much more accurate estimator, and here is its formula for the error. So this time, your k involves the fourth derivative. So if I ask you to do something like this, you really should use something to find the fourth derivative, like Wolfram Alpha calculator. I'm totally serious. Like, I'd give it to you. All right, so how large should we take n in order to guarantee that with the Simpson's rule approximation for 1 to 2 of 1 over x dx is accurate to 0.001? Now we did this with Trapezoid Rule and with the Midpoint Rule, and those I believe were 41 and 29 respectively. Simpson's rule is going to be 7. It's amazing how accurate this is. So first thing is find the fourth derivative of f of x equal 1 over x. So the fourth derivative of x is 24 over x to the fifth. And on the interval from 1 to 2, this is largest at x equals 1. So we take k to be 24. And then the absolute value of the error of the Simpson's rule is less than or equal to 24 times 2 minus 1 to the fifth over 180 n to the fourth. And the reason that you can use so many fewer terms is what this error estimate tells you, and how you can tell from the error estimate is that the denominator has a larger number and that n to the fourth down there also contributes. This needs to be less than 0.0001. So multiply the 180 n to the fourth over, and we'll have 24 is less than 0.018 n to the fourth. Divide by 0.018 and we get 133.3. It's less than n to the fourth. And now if we fourth root stuff, so fourth root of 13, 1333.3 is less than n, and you get 6.04. And because you only can take whole numbers of intervals, and because your n has to be bigger than 6.04, you have to round up and say, oh man, n is bigger than or equal to 7. So only 7 pieces, only n equals 7 to make Simpson's rule work. And actually, one technicality is Simpson's rule, your n must be even. So in actuality, you must take n bigger than or equal to 8. And the reason that you have to do this is so that pattern with the coefficient works out, which comes from the fact that you've got to fit little parabolas to everything. So Simpson's rule must be even n. So let's use Simpson's rule with n equals 10 to approximate this curve that area of this curve that we did earlier. So once again, delta x will equal 2 minus 0 over 10, which is 0.2. And so S10 is delta x over 3, so 0.2 over 3. And then we plug in 0, e to the negative 0 squared. Then 4 plugging in 0.2s. And then 2 plugging in 0.4. And then 4 plugging in 0.6. You get the idea. All right, and the second to last thing, we plug in 4 of them, and that's e to the negative 1.8, and then plus e to the negative 2 squared. I didn't put parentheses there. As long as there are no parentheses around the negative, by default it means the negative is not squared. This is approximately 0.882. And let's find the error in this estimate. So I used Wolfram alpha to get the fourth derivative. So the fourth derivative I got that this was 4e to the negative x squared times 4x squared must be 4x to the fourth minus 12x squared plus 3. And I found that the max was 12 on the interval from 0 to 2. I just graphed it and looked at it. So then the error for Simpson's rule, absolute valued, is less than or equal to this k, which is 12, times b minus a, so 2 minus 0 to the 5th, over 180 times n, which is 10 to the 4th. And that is about equal to 0.0002. So worst case scenario, you're off by hundreds, tens, thousands. You're off by 2 10,000s. That's not very much.